So I want to evaluate the Fourier series of the function that is defined as 1 between 0 and pi and -1 between pi and 2 pi. And of course this is 2 pi periodic. So as usual I will first find my complex Fourier coefficients Cn, and then I will find my real Fourier coefficients using those complex coefficients. So as usual I have the integral from, I have 1 over 2 pi times the integral from 0 to pi times of 1 times e to the negative I n x. Okay, that is my complex exponential because I have here the complex Fourier series, the complex Fourier coefficients, minus, because there's a minus here, the integral from pi to 2 pi of this, this minus 1, the minus we took it here, times e to the minus I n x dx. Okay, so that is just this is the integral from 0 to 2 pi, but because we have two cases, okay, one between 0 and pi and -1 between pi and 2 pi, we need to split that up into two integrals. So now we evaluate. It is easy. We have just an exponent that we need to evaluate. So remember to evaluate that. We e to the ax, if we evaluate that, if we take the integral, this is simply e to the ax over a plus a constant, of course. Yes. And before that, we will also just switch the integral boundaries here so that we get a plus here, okay? So we will switch the pi into 2 pi, so we get the integral from 2 pi to pi, and you get the plus here, okay? Because we have a -1 here, and if you switch the boundaries, we also get another -1, and so we get a positive, okay? Remember that the integral from a to b is equal to negative the integral from b to a. That will make life a bit easier. And here everything is the same. So as said, now we just integrate our exponential, and then we get this e to the minus I n x as usual, as before, over minus I n. Okay, that is simply the coefficient here in the power of this exponential. Okay, and so now we evaluate it first between 0 and pi, as here, and then between 2 pi and pi. Okay, as here. Because now it's the same. If we didn't switch this integral here, if we didn't switch the borders, it would be similar, but you would have a negative sign for the second integral, and it would be from pi to 2 pi. And so if we can just switch the signs so that we get the 2 times the same integral, just with other border values, that's better to deal with. Okay. So if you plug that in, so this pi, 0, pi, and 2 pi, we get this 1 over 2 pi again times -1 to the nth power. Okay, because if you plug in a pi here in this e to the minus I n x, this alternates. Okay, for n equals 0, it's 1. For n equals 1, it's -1. For n equals 2, it's again 1, and so on. And for this other pi here, this is the same thing. We also get the same thing. This -1 to the nth power over -I n, and then we get minus, because it's the bottom values of the integral we evaluate, minus this. If we plug in 0 and 2 pi, we get 1 here for the e to the minus I n x. Okay, if you plug in 0, you have e to the 0, that is 1, and if you plug in 2 pi, we get e to the minus I n 2 pi, and if it is 2 pi, we always come back to the 1 at the beginning, okay? Never the -1, okay? Never here. And so we get minus this 1 over minus I n, okay? This is simply the 1, as said here. This is simply 1. Here too, and the minus comes from, as said, because the values here are the lower boundaries, okay? It comes from that. And so now we can rearrange a bit. We have 2 times the same value here and here. So we have a 2 here in the denominator, so they cancel out each other. So you can factor out the 2, and then it can cancel out with this 2 here. And you are left with 1 over pi, okay, this 1 over pi, times this -1 to the nth power over -I n, okay, this one here. Now, because we factor out the 2 that cancel with this one, so this value and this value are the same. So now there's only one value, because as I said, we factor out the 2. And then we have this plus 1 over in, okay, because we have negative 1 over negative in, so negative, negative, so positive. And again, we also factor out the 2 here, I said, that cancelled with this 2 here in the denominator here. And yeah, so we are left with 1 over pi. We are left with 1 over pi times minus 1 to the nth power over negative in plus 1 over in, okay. And now this thing is 0 is if n is even, okay. If you have like 2, we get 1 over negative in, so negative 1 over in plus 1 over in, so 0. And if it is odd, so if we have like 1 or 3 for n, or I don't know, 27, yeah, it's odd, so it is negative here, but there's also a negative sign here, so we have positive, so we have 1 over in, and you also have a 1 over in here, so we have it 2 times, and so we get 2 over pi in, okay. And as usual, you can see that there is a n in the denominator, so this thing is not defined for n equals 0, okay? If we plug in n equals 0, we divide by 0, so that is not possible. So we need to evaluate the complex Fourier coefficient separately for n is equal to 0, okay? Because all other values you don't get something undefined because you don't divide by 0, but for n equals 0, you divide by 0. So we evaluate this c sub 0 separately, and so we plug in simply n is equal to 0, and so we simply get 1 here, instead of this e to the minus I n x, okay? We simply get 1, because it's e to the n equals 0, so we get e to the 0, and that is simply 1, okay? And so we are simply left with the integral from 1 over 2 pi times the integral from 0 to pi of x, minus the integral from pi to 2 pi of x again, but now again we can change the integral values, we can switch them as seen here, and we have also plus the integral from 2 pi to pi of x, simply for the second case, okay. First we have like we have this 1 over 2 pi, then you have 0 to pi x dx minus pi 2 pi x dx, okay. And so again we can switch those two boundaries, and so we get another negative one, another negative sign here, and so we get positive, okay. We get minus minus, so positive 2 pi to pi of x dx, okay. And so if you evaluate that, we get 1 half plus 0 plus 1 half minus 1, okay. So pi, if we plug in pi, we get 1 half, because there's this thing here that we need to consider. Then we plug in 0, we get 0, because there is an x here, so we get 0. If we plug in x is equal to 0, then we get another pi, okay, so again 1 half, okay, 1 half here. And then we plug in 2 pi, but remember this is the bottom value, so it is negative, so if we plug that in, we get negative. So we get negative 1, okay, so we get negative 2 pi over 2 pi, so negative 1, okay. Again, also for this 0, this is a negative value, but because this is 0, we don't really care, because we get 0, okay. So our c sub 0 is simply 0, okay, so it wouldn't have changed anything if we had forgotten it, but it wouldn't have been completely correct, because we didn't know that we will get 0, okay, so we still need to do it. Okay, for each case that our general value is undefined, that is, we divide by 0, we need to do it separately, okay. Generally it is 0 because we have something like something over n, like here, but it can also be something like something over n plus 3. In this case, you need to do the case n is equal to negative 3, okay, because if n is equal to negative 3, we get negative 3 plus 3, so 0, and you have a problem. But for this case, of course, you don't need to do the case for n is equal to 0, because we will simply have 3 in the denominator, okay. Yes. So our a sub 0, now we can convert our complex Fourier coefficients into our real Fourier coefficients. So first, our a sub 0 is 2 times c sub 0, which is simply 0, because our c sub 0 is simply 0. So we don't have any a sub 0. Our a sub n is simply c sub n plus c sub negative n, okay. So for this case here, this c sub negative n, we simply replace each n with the negative n. and so that is was our value here. So this 2 over pi I n, and so we also get 0 because we have our first our stuff with the n, and then plus the same stuff, but instead of n we have negative n, so we have 2 over pi I n plus 2 over pi I negative n, so 2 over pi I n minus 2 over pi I n, so simply 0, okay? And for the b sub n, we have I times, in parentheses, c sub n minus c sub negative n. And so if you plug in everything, this I here cancels with this I here. And now we have the same negative as before, c sub negative n, but you have a negative sign in front of it, so it inverts the sign and we get 2 times positive, okay? And so we're left with 2 over pi n, okay? We're left with 2 over pi n. And so our real Fourier series is simply 1/2 a sub 0, so that will be 0, plus the sum from n is equal to 1 to infinity of a sub n times cosine of nx plus b sub n times sine of nx, okay? And so I said our a sub 0 is simply 0, so we don't have anything. Our a sub n is also 0, so we don't have anything with cosine. And our b sub n is this 4 over pi n, okay, here. And so at the end you're left with the sum from n equals 1 to infinity of 4 over pi n times sine of nx, okay. And remember n is odd, okay, as stated here, if you can still read it. If n would be even, we would simply get 0, because I said here we would have 1 over in minus 1 over in, and yeah, we would get 0. So n is odd. So you could rewrite it if you want as like set n is equal to 2m minus 1, where m goes from 1 to infinity. Okay. Yeah, I don't know. Anyway, so you could rewrite this result here as the sum from m equals 1 to infinity of 4 over pi times 2m minus 1 times sine of x times 2m minus 1. Okay, so those are parentheses, and this two here also, of course. Yeah, so you just replace every n with this 2m minus 1, because I said n is odd, okay? That is an odd number, this thing, okay? Because you can plug in every value you want, you will still always get an odd number, okay? Like if you plug in 1, you get 1, if you plug in 2, you get 3, if you plug in 5, you get 9, if you plug in 6, you get 11. Yes. So as usual, yeah, you split your integral into 2 pieces, because it has a different value depending on where it is between 0 and 2 pi. So you evaluate it, use the complex Fourier coefficients, because it's easier to deal with an exponent to integrate than with cosine and sine. And then once you got your abstract value, be sure to check if it is defined for n even or n odd. Okay, remember n is simply an integer. And then find the values where it is undefined, where you divide by 0, and you need to do those values separately. So here we had 1 over in, some 2 over pi in, sorry, 2 over pi in. So if n is 0, we divide by 0. So we need to consider this case separately. And so for that, we evaluate the integral separately. Simply we plug in this n equals 0, or whatever value it is, inside this e to the negative inx, and then we calculate our integral, okay? And yes, then you find your a sub 0, which is 2 times c sub 0, or a sub whatever number causes problem here is equal to 2 times c sub whatever causes problem here, okay? Here it's 0, I said, but it could be something else, like here it could be a -3 or whatever. And then your an is simply c sub n plus c sub negative n, and your bn is I times, in parentheses, c sub n minus c sub negative n. yes, and your a sub n basically is the even part of your result, and the b sub n is the odd part of your result. Okay, so here if a sub n is 0, we know that this thing is not even. Okay. Yes. Yeah. So it is logically odd because we have our b sub n. Okay. Logically. Anyway, and then you plug everything into your final result. So 1/2 a sub 0 plus sum from 1 to infinity of a sub n times cosine nx plus b sub n times sine x. You plug in everything. Okay, I said here in your case a sub n is 0, so we don't care about it. We are only left with the b sub n. And yes, let's remember at the end to write that this value is only defined for n odd or n even or whatever, and then you can rewrite your if you want replace your n with 2 m's minus 1 n m between 1 and infinity. If it is odd, and if it is even, simply replace it with n is equal to 2m. Yeah, m is between 0 and infinity, or 1 and infinity. No, sorry, 1 and infinity, because the 0 case is always it's what? I think it's between 1 and infinity, but it is because yeah, here or a sub 0 is considered separately because we divide by 0. If your yeah, a sub 0 is not a problem, you can go from 0 to infinity, except the number that causes problem. I don't know, like here, if it is -3, so it is yeah, it is between yeah, 0 and infinity, except for n equals -3, or then yeah, m equals I'm a bit trouble. Anyway, before I say something wrong, yeah, I forgot about this part. Just if it's odd, n is equal to 2m minus 1, m is between 1 and infinity. For even, yeah, I don't know. Anyway, yeah, I hope it was clear, and sorry for the troubles. And yes, thanks for watching.